Fine. Okay. Hi, I'm Leif. I'm doing my PhD at the Heidelberg Institute for Theoretical Studies, and I would like to present some work on our machine-learned molecular mechanics force field. And this is work done together with Erik Hartmann, Jan Stümer, and Frauke Kreta. Yeah, first of all, what is a force field, or what do I mean by a force field? It's essentially a map from atomic positions and elements to potential energy of a system. And there are different methods around, and these methods all have a trade-off between computational cost and accuracy. So you have quantum mechanics. This is very accurate, but also very expensive and has relatively bad scaling for large systems. On the other side of the spectrum, you have molecular mechanics, where you essentially describe your molecule with classical physics. And this is very efficient, but also has bad accuracy. And this tension was somewhat lifted in the recent years by E3 equivariant neural networks, which are much cheaper than quantum mechanics, but almost have the same accuracy, or at least somewhat get close to it. Yeah, but still they are orders of magnitude more expensive than molecular mechanics. So what we did is we used machine learning to improve molecular mechanics, and then you get a force field that is more accurate at the same computational cost. So, molecular mechanics. As I said, you describe your system with classical physics. So you go, first of all, from 3D coordinates to 2D. So you represent your entire set of conformations, the whole molecule, with a 2D molecular graph. Then you express the potential energy as sum from different contributions, for example, from bonds, and for this, like from bond stretching. And for this contribution, you use a physics-inspired simple functional form, for example, a harmonic potential. And there are 3 parameters in there. For example, in the harmonic potential, you have the force constant and the equilibrium distance. And these are 3 parameters that need to be adjusted for every molecule. Now, molecular mechanics has 2 sources of error. One is that you describe a quantum mechanical system with classical physics, and the other is often a non-optimal choice of 3 parameters, and this is where machine learning can help. So for the second source of error, if you learn the parameters directly from the molecular graph, you can improve that. Yeah, that's what we did. And here's the idea how this works. You start off with a molecular graph. Then in the first step, you use a graph neural network to predict atom embeddings that still live on this molecular graph and represent the local environment around each atom. And then you see the output down here are properties of subgraphs. Each of the subgraph corresponds to one of these contributions that you saw earlier. So this would be the bond contribution. You also have contributions from angles and also contributions from torsion along bonds. So what we have is we have 3 different models that share a similar architecture but are, have different learnable weights, and they use these atom embeddings to predict properties of these subgraphs. And the model that we designed for this we call a symmetric transformer. Now, why is symmetry important here? This map psi from atom embeddings, which we call nu here, to mm parameters should have certain symmetries that are given by physics, essentially. Because if you look at a single angle, then it should not matter when you permute the outer atoms. It's the same subgraph, so the energy contribution should be the same. So this symmetric transformer model that we have should automatically have this symmetry that if you permute the outer atoms, then it will be the same. Okay, we do this by using a permutation equivariant model, so permutation equivariant layers, which essentially means if you apply a permutation pi on the inputs, then this will also have an effect on the output, so the outputs will also be permuted. And then in the end, you can use a pooling operation, for example, sum over all permutations, and then you have the desired permutation invariance. Now, this is a bit too much. We don't want invariance over all permutations, but only these special permutations. So, for example, if you permute an inner atom with an outer atom, the model should be allowed to predict something different. And to enable this, we use a symmetry breaking positional encoding. So for example, for this angle contribution, we would assign a 0 to the outer atoms and a 1 to the inner atom. Then this is symmetric under the permutation where we actually want invariance, and not symmetric under the others. So this will increase the expressivity of our model. Okay, this is how the model looks like then. For the permutation equivariant layers, we use a normal transformer architecture. Here you see the colors really don't work out so well. Here you see the positional encoding that I was talking about, that you already append to the features at the very beginning, and it depends on the type of subgraph. And on the right side, you see pooling operations that essentially then make the output invariant, not equivariant, with respect to these permutations. The last layer is a mapping to an interval, because you know from physics that MM parameters need to have a certain range. For example, force constant should be positive, equilibrium angle should be between 0 and pi. This we enforce there. Okay, we call this architecture GRAPPA for graph attentional protein parameterization, but it's more general than proteins, as you will see soon. We trained it on over 14,000 unique molecules and 800,000 states. With states, we mean QM energies and forces. So we predict MM parameters, then we have a differentiable implementation of the MM energy function, and then we can directly end-to-end learn energies and forces. And our data set, and thus also the force field, covers drug-like molecules, peptides, RNA, and peptide radicals, all in one consistent force field. And it's available for use in the popular MD engines, GROMACS and OpenMM. Okay, how does this look like? These are the predictions on a test data set of our model. So in red, you can see an established molecular mechanics force field. These are highly specialized to the type of molecule. And in blue, it's our model, GRAPPA. Down here are the forces, here are the energies, and the y-axis is the prediction, the x-axis is the quantum mechanical reference data. So you want to be close to that diagonal. And you can see that accuracy is somewhat improved. The same thing you can see in this table. So this represents the same data. Over here, you can see the established MM force fields. Here are the test RMSEs of GRAPPA for both energies and forces on these test data sets. And here is essentially the mean, or the standard deviation of the whole data set. And down there, the same data again, at least on this right point. This is what happens when you shrink down the training set. So even if you only have sparse amount of data, you're still better than these red lines here, which correspond to the existing molecular mechanics force fields. And there's also another machine-learned molecular mechanics force field. It's called S-Paloma. And yeah, we included it in the table as well. And one of the nice things is that our force field is quite general, so it only really needs a molecular graph, connectivity, and element types to make its prediction, so we can apply it to uncharted regions of chemical space, and we demonstrated this by applying it to radicals. Okay, now, can we a bit better understand how GRAPPA makes its prediction? This would be nice. So what we did is we looked at the latent space of our model, which is 256 dimensional, but you can project it down to 2 dimensions by doing a principal component analysis. And then you see that, at least for the elements that are contained in the data set, our model somehow implicitly learns the periodic table, which is not part of the input, so we only give a one-hot encoded element, so there's no notion of distance in chemical space, and we can see here that it is learned. Here you would see the first period, there the second, and from the third period we only have one element. So it's somewhat reasonable and similar to maybe what a human would also do if you want to parameterize molecules. Okay, what happens if you apply this to large molecules like proteins? A problem of machine-learned force fields, but also quantum mechanics, is that sometimes your molecules explode during simulation because you simply transfer, or you the path, your trajectory goes out of the validity, out of the region of validity of your force field. So it would be nice if we can somehow ensure that this doesn't happen. And here in Grappa, the nice thing is that we use molecular mechanics. This already helps because you have these harmonic potentials, so it will keep things together. And if we simulate a protein in water, this is about 70 residues, so in total 2,000 atoms, we can see that the AMLD of our model, or of the simulation with our model in blue, and the one of an established protein force fields, they both don't explode, at least for 100 nanoseconds. And actually, our force field even keeps the protein a bit more stable, so there are less fluctuations on smaller timescales. What happens if we go away from the folded conformations of the protein? Even if we start from an unfolded state, during an MD simulation, our force field folds this small protein. It only has 10 residues, but you can see that you start at a high RMSD, and then in terms of microseconds, the protein gets folded during MD simulation with our force field. So it also captures the physics that somehow lead to this folding. Yeah, and we believe that this increased accuracy at the same efficiency, while still retaining macro observables, is a good argument for using for at least trying it out in MD simulations of biosystems. Yeah, thank you.